Okay, kita dah discuss last week. We have discussed about the division of load between two generators. So the last 2 weeks before your midterm semester break. Okay, we have looked at this example. Now we proceed with the model of our components. Okay, so basically for real power control, we want to look at what happened in the generator itself. So this is for generator models. So we look at every models and then we look how we develop the block diagram or model for the complete system. And then next class we will look at in details how we will deal when the load changes in the system. So in the when we consider the tie line and so on and so forth. Okay, so basically this is generating unit model. So we have in terms of the block diagram basically. So we have a mechanical input, okay, mechanical energy input. So the turbine will rotate. So we have the Tmac, and then normally T mechanical and T electrical will be contradict each other in order to produce the electrical energy for the generator. So this is the simple block diagram from the mechanical input to the electrical energy output. Okay, the generator driven by steam turbine can be represented as large rotating mass with two opposing torque. That's why it's contradict between the mechanical torque as well as electrical torque. Okay, so Tmac represented by the mechanical torque acts to increase the rotational speed, where the T-elect act to slow it down. Okay, so this contradict each other. So when they are in equal magnitude, the rotational speed omega will be constant. Okay, when your Tmac equal in magnitude with T-elect electrical, so the rotational speed omega or frequency will be constant. When we have the electrical load is increased, meaning that your T-elect is greater than Tmac. So what happens is your entire rotating system will begin to slow down. Okay, and then since it will be damaging to let the equipment slow down too far, something must be done to increase the mechanical torque in order to restore the equilibrium, to make sure that your Tmac will equal to the T-elect. So that's why you need to increase the mechanical input. Okay, ini contoh itu. Okay, so this is just the definitions. So normally we look at the omega is rotational speed in terms of radian per second. And then we have the alpha, this is rotational acceleration. We have delta, phase angle, rotating machine. So T net is net accelerating torque in machine. Okay, Tmac mechanical torque, T-elect electrical torque. And then we have P net is a net accelerating power, Pmac mechanical power output input, P-elect electrical power output. And then we have moment of inertia, I, and M is angular moment for the machine. Okay, basically all quantities is per unit on the machine base. Normally your angle in terms of degree, but everything we measure ataupun we do the calculation within the per unit. Okay, and then your omega we measure standard system frequency base. Thus your M is per unit power per unit power per unit frequency per second. Okay, and all steady state nominal values with zero subscript. So if you have nominal values or the steady state represented by the not, okay, zero. And then all changes for nominal will be designated by delta. So let's say we have delta omega, delta P, and so on and so forth. So for power, delta P. Okay. So this is the model. From that particular block, we can model our generator in terms of Pmax and Pelect, where your Pmax and Pelect normally will contradict each other. So we have delta Pmax, meaning that you have the difference of the mechanical power must be plus minus, meaning that it's minus Pelect, and then you have the block diagram here in Laplace transform. If you remember, Laplace, and the output here will be delta omega. So from this model, basically we can express the equation where delta Pmax, because this is plus, this is minus, so plus minus. Okay, that's why you get this value. This equation equals to omega naught I d omega over dt. So you do the derivation of delta omega with respect to dt, and basically you can get Laplace lah. Yang ni you kena refer back. Ingat tak you belajar Laplace dulu? You belajar Laplace berapa kali? Ingat je ni. Ada orang tak? Ingat tak kelas you belajar Laplace berapa kali? You belajar Laplace dekat matematik sekali, dekat saya tak ingat. Patut you belajar 2 kali. Signal and system pun you belajar juga kan?
Ya, Doktor.
Kan? You belajar 2 kali, so you dapat. When you do you have the time domain, and then in terms of frequency domain, you do the Laplace. And then when you do the operation in the frequency domain, and then you inverse balik ke time domain kan? Kena refer balik lah. Okay, this is the generator model. So later we will look at how we can develop the complete system lah. So this one is the generator model, where we have mechanical input minus dengan electrical delta P. So this is the rotating in terms of Laplace transform 1 over ms. So this output is delta omega. Okay, and then we move to the load model. So we have the load model. Normally we have a variety of electrical devices. Okay, purely resistive. So we have resistive load, we have motor loads with variable frequency characteristic, and etc. Okay, the change in electrical power is governed by the change in load. Normally when we say the load changes, so in terms of electrical power lah, sama ada you increase ataupun decrease. Okay, we have 2 types of load. So we have non-frequency sensitive load, delta PL. So this is the representation, delta PL, bukan loss lah, load, PL, meaning that this is the purely resistive loads. If we have the depend on the frequency, so we have the notation here, frequency. So example, our motor, in terms of normally is dominant in electrical loads lah. So basically our load is not purely resistive lah. That's why sometimes you have a capacitive and also inductive. Okay, that reflects to the frequency. So since motor load are dominant part of electrical load, there is need to model the effect of change in frequency. So as you can see that your generator also with the effect of frequency here. So we can see that our load model also with in terms of frequency changes. Okay, and then the relationship between the change in load due to change in frequency is given by delta PL, frequency, is D times delta omega. Okay, your D, where you can rearrange this equation. So jadikan D sebagai tajuk. So you get D equals to delta PL divided by delta omega. So in the net change in P elect, meaning that your changes in the electrical power is equals to, this one is delta PL that not related to the frequency. This one is delta PL that have effective from the frequency. So yang ini kita just tukar je lah. So your delta PL is D omega, where your D is load damping constant. Okay, this is load damping constant. Dia ialah your P elect basically consists of 2 parts, that your load changes, that the pure resistive, and the other one is the effect from the frequency. So that's why you have delta PL plus D delta omega. Okay. So when we want to do the model, normally from this equation, okay, so similar, we have delta Pmax, delta PL. Yang kat sini ialah delta Pmax, delta Pelect. So this is the your generation, right? So this one is your load. So this one you have a load changes here. So since kita punya system ialah 1/ms plus this one is you have a feedback. If you remember, dulu belajar control system kan? Ingat tak belajar control system? Bila you ada feedback, you boleh rearrange the equation to become a linear kan? Ingat tak? So yang ni feedback, and then you boleh rearrange this block into this equation. Okay? So this is the block diagram of rotating mass and load seen by prime mover unit, prime mover output. Okay, so from here we can see that the system block including the effect of load damping, D. And then the absence of speed governor, the system response to load change is determined by initial constant. Kita tengok ni lah. So for example, just a simple example, we have an isolated power system with 600 MVA generating unit having M, your mass rotating is 7.6 per unit megawatt per unit frequency per second on machine base. The unit is supplied of 400 MVA. So your load is 400 MVA. The load changes by 2% for a 1% change in frequency. Okay, meaning that the load changes by 2% for each 1% change in frequency. So find delta omega after increase of load by 10 MVA. So suddenly you have delta PL 10 MVA. So how we want to find the delta omega? So using this one. So basically to find your D, your damping, is load change divided by frequency change. Kan? P, load change divided by frequency change. So that's why you get your load change is 2 MVA or 2% terms of per unit for one frequency change, right? So you can boleh bagi 2 bagi 1 dapat 2. Your D is 2. And then you need to convert into the base. So change in D and M based on 2 new base. So this one, everything we change to 1000. This is tip. Make sure that the whole system is 1000 MVA base. Maknanya you kena tukar everything, your components to 1000 MVA. So yang ni you kena pakai balik, you kena dapatkan balik kau ni cara tukar base dekat EPS yang you dah belajar. Okay, so that's why cara dia ialah this is at the old value, right? So your 400 MVA is equals to 2. Now is 1000, right? Terbalik 2%. Okay, so 400 divided by 1000. Balik 2 divided by this one, supply is 400 and then system is 600. So 400 divided by 1000 is times 2. So dapat dengan 0.8 lah kalau 1000 MVA. Tips, the reference bukan terbalik. Reference dia ialah 1000, tapi sekarang ni you punya value is 900, 400. Okay, so pada 1000 MVA 2, now is 400 MVA berapa? System now is 400, so 400 divided by 1000 times 2, so that's why dapat 0.8. Okay. Sama juga untuk dia punya M, system is 1000, so 600 divided by 1000 times 7, so dapat 4.56. Next you need build the block diagram for the load diagram. So we have delta Pmax, delta PL. So this one is your 1/ms plus D, right? So gantikan. And then find the drop in frequency, if nominal frequency is for 50 Hz. So yang ini from here you boleh guna this equation. This is data Pmax minus data PL times, because this one the block jarak dengan block diagram ni kau dapat output kan. So this one in term of Laplace 1/4.56s plus 0.8. So data Pmax is currently is not changing, so meaning it's 0, but your PL is 10 MVA, right? So 10 MVA divided by 1000. That's why dapat 0.01 lah per unit. So and then you buat dalam Laplace is 0.01/s. So when you get you solve this solution, this equation, you get minus 0.01 divided by 4.56 s square plus 0.8 s. Okay. So daripada sini you kena inverse guna, this one is in frequency domain, so you need to change into the time domain. Ingat tak dulu you belajar Laplace dulu, you inverse Laplace?
Tak ingat dah.
Kena ingat balik lah, saya pun tak ingat. So dia kena rearrange the equation kan, equation ni kena rearrange supaya dapat you kena ada dia punya table, betul tak? So bila you buat in time domain, that's why yang ni saya rasa you kena rearrange, saya pun tak ingat. So you dapat kena buat something kat sini. Dia ada dia punya time domain kan, divide by 0.8. So dia ada dia punya constant dia, saya pun tak ingat. So at the end of the day dapat yang ni lah, 0.01 divide by 0.8. 0.48 divided by 4.56 T. Kena refresh balik, saya pun tak ingat lah, lama dah ni. Minus 0.01 divided by 0.8, so dapat function of omega with term of time domain, this one lah. Okay, so dapat 0.0125 E minus 0.175 T minus 0.0125. Okay. Okay, the final value delta omega is minus 0.0125 per unit. Kenapa? Saya pun tak ingat. Kenapa jadi gini ya? Dia check balik lah. So dia ambil 0.0125 is the delta omega, and then jarak dia dengan 50, so frequency drop, nominal frequency 50 Hz, now is drop to 0.6, maknanya 50 minus 0.6, now your frequency bila load suddenly enforce 10 megawatt ataupun 10 MVA, your frequency from 50 drop to 5, 7, 9 tak nak 3, so 49, 1375 Hz lah. Bila ada 10 MVA in the system suddenly change your load. Okay, load changes lah. So ini load model. Okay, boleh lah. Apalah, yang ni you tak ingat pun tak apa, sebab ini just how we model it. Kita takkan go detail lah, sebab you dah belajar dekat kelas sebelum ni kan, untuk soal apa ni, soal kelas. Okay, now we move to the prime mover. So we try to finish everything in terms of the model, and then kita akan cuba tengok macam mana kita can construct the system, we build the whole system in terms of block diagram. Okay, boleh lah. Okay, masuk dia lambat ni. Okay, this is prime mover. So prime mover is used for driving the generator unit, steam turbine or hydro turbine. So the model of prime mover must take account of the steam supply and boiler control. So this is part of mechanical part, meaning that kalau tengok kat sini, kita punya generator kan, turbine kan, so kita ada mechanical punya this one, Pmax. So input kepada Pmax ni apa? This one output, right? Pmax. So apa yang jadi daripada Pmax tu, dia ialah daripada dia daripada kita punya prime mover. Okay, this one is simplest one lah. So we have your delta valve. Maksudnya kat sini bila you ada perubahan load, your load suddenly increase, now your frequency not equilibrium, maknanya frequency akan jadi slow kan. So dia akan open the valve to make sure that there is input, more mechanical input to make sure your Pmax is increased, to make sure that your frequency is always constant lah. So this is a block diagram for prime mover. So you have 1/1 plus STTH. This one is changing time constant. And delta P valve is the per unit change in valve position from nominal. So dia buka tutup you punya valve kat generator. Okay, so kita boleh model kita punya sistem. Okay, so kalau tengok sini dia prime mover, generator, load model. So kita ada prime mover. This is prime mover. Output, this one Pmax. And then kita ada load model. This is our load model. Kan? Yang tadi kan? So prime mover, generator, load model. Okay, and then delta P valve ni kita kena tengok in terms of macam mana kita nak measure the speed. So kita pakai governor lah. So governor, kita modelkan governor kita. This is the governor model. Governor is the mechanism that sense the machine speed. Bila berlakunya perubahan speed tadi kan, bila load enforce, the system speed become slow. So governor lah yang akan sense and then adjust the input valve. So dia akan adjust the input valve ni. So maknanya kita akan tengok yang belakang lagi sebelum valve ni lah. Okay, adjust the input valve to change the mechanical power output to compensate for load changes, to restore the frequency to nominal value. So paling simple kita pakai asynchronous governor lah. Okay, ni paling simple. Tapi sekarang ni biasa pakai computerized lah. Okay, suppose the generator unit is operated with fixed mechanical power output from the turbine and then any load change will result in speed change. So sama ada load berkurangan ataupun load bertambah. Kalau load berkurangan, your speed become faster lah. So maknanya dia kena tutup valve. Okay, so this will cause the frequency sensitive load to exact compensate for the load change. So meaning that you want to compensate back what will happen to the load change. This condition will allow system frequency to drift outside acceptable limits. So suddenly dia akan certain amount of time dia akan varies in terms of the accessible limit, but it's not cannot be prolonged lah, tak boleh lama. So that's why kalau bila kadang suddenly you become heavy load, so there is auxiliary system yang akan cut off ataupun make sure that your system is within the specs supaya boleh protect kita punya equipment lah. And then overcome by adding the governor mechanism. So that's why we need to add the governor mechanism, sense the machine speed and adjust the input valve to change the mechanical power. Okay, and then nowadays we pakai TMB ataupun any IPP pakai electronics lah, pakai sensor. Ni contoh. So we have, this is a reference when we have, this is contoh asynchronous governor So kita ada prime mover, steam valve. Ni cara dia buka atau tutup. Okay, so let's say we have speed measurement device. This is rotating shaft. Let's say we have plus minus. Kalau you system suddenly the load suddenly happen, tambahan 10, katalah tadi macam tadi contoh 10 megawatts is increase. So suddenly your punya frequency ni akan slow kan. So plus minus dia akan dapat negatif. Betul tak? So plus minus, let's say our reference is 50 Hz. Suddenly this one become 49 something. So plus minus akan dapat negatif. Your delta is become negative. And then you ada satu gain lah. Gain kat sini dia buat negatif. Maknanya inverse negatif. So darab negatif dapat positif. And then this 1 kg also gain. So bila positif, and then this is the integral punya function. Kalau positif dia akan open valve. Maknanya supaya your valve akan allow more steam to make sure that your prime mover become faster to meet the demand. Maknanya bila berlaku load tadi, katalah delta P load tadi suddenly up 10 megawatts. Bila kita kira tadi dapat 49 something kan. So plus minus akan dapat negatif. Negatif akan dapat positif, and then you gain, and then you do integral dapat positif. Positif open the valve. Open the valve, steam akan masuk banyak So prime mover akan laju supaya meet the make sure that our speed as close as to nominal. So katalah bila dah up, your frequency become 50. So akan jadi kosong kan. Kosong tidak ada apa lah. Maknanya dia akan maintain your stuff, your valve. But let's say we have suddenly load to decrease from 10 megawatts become minus 10. So let's say minus 10 megawatts drop. So your frequency akan jadi laju. Katalah dapat 50.5. So when you plus minus with reference, dapat 0.5 which is positive kan. And then darabkan negatif, and then you gain integral bila negatif, dia close valve. Maknanya dia akan tutup valve supaya prime mover akan slow. Okay, itu cara governor beroperasi. Boleh? Okay, macam tu tadi negate and amplified by gain kg. So delta P valve which cause the main supply valve to open when negative. Kalau negatif dia akan negatif, dia akan jadi positif, and then dia gain kan. So positif akan buka. Okay, kalau positif akan jadi negatif. So dia akan negatif, dia close the valve. Okay. Ini apa yang saya katakan tadi lah. Ini contoh kalau load increase, omega will fall, so dia akan dapat negatif yang tadi saya dah cakap tadi. Okay, we use the feedback signal that cause the speed error to go to zero at different value of generator output. So this is accomplished by adding the feedback loop. So sometimes kita kena control dia supaya dia dapat speed error to go to zero lah. Make sure that's why kita kena ada sistem yang akan feedback. So you ada load reference set point. Betul, you ada sama ada nak buka atau tutup, make sure that always in terms of the governor is your frequency is always in the equilibrium. So that's why kita akan ada satu kita panggil feedback group R. Okay, so dia akan bagi balik kat sini in order to make sure that we can achieve the error to go to zero. Okay, so this is net gain 1 over R. 1 over R maksudnya kat sini. Okay, so ni contoh kalau kita governor with group model lah. So let's say we have group model. This one is just a simplification of the block diagram kan. Ni delta P valve ni ialah yang masuk kat sini lah. Right, sini. Okay, you kena relate everything Kita start dengan generator, and then load, and then prime mover, and then governor. And now governor with group pada feedback. Yang ini kita boleh buat equivalent ni. Ingat tak belajar dulu dekat control? Ingat tak belajar kat control bila kita nak move the block diagram ni, kita nak bawa ke sini, apa akan jadi? You belajar dulu kan dekat control system.
Belajar doktor. Nanti dia akan
like
tambah lagi satu
R, and then you kena play around with this one. Because this one we bring everything here. So this one R kita bawa ke sini kan. So dapat 1 over R. So yang kat sini kita kena buat simplification. Ingat? Saya dah tak ingat lah. Sebab saya tak ingat ada control system. So basically yang ni lah. Ni yang berlaku. So kita ada load reference. Okay. They bring everything here from this part to this part. Dia bawa sini in order to make sure to simplify the equivalent ni lah. And then at the end of the day, you dapat this one value. So this one is your speed reference delta omega, and then you have group 1 over R, and then you have load reference, and everything ni ialah dia bagi simplified of TG, governor time constant 1 over kgr ni. Okay, so you dapat output delta P valve. Okay. Okay, so the result of adding the loop, we get R is governor characteristic. So what happened? So the value of R determine the slope. The slope of R characteristic. R determine the changes on the per units output of a given frequency. The frequency, the output. So common practice to set R on each unit so that the change from the 0.100% rated output will result the same frequency. So make sure kita cuba dapatkan everything is the same frequency. Okay, as a result, a change in load in system will be compensated by generator unit. Output changes proportional to each unit. And everything, the load changes, everything will work accordingly. If two generators with grouping governor characteristic are connected to power system, there will be a unique frequency which share load. Ni yang kita dah discuss hari tu lah. Kan, bila ada dua yang kita buat segitiga punya karakteristik tu. Yang ini akan masuk test lah. Satu soalan. Next weekend. Okay. So macam ni lah konsep dia. Okay, so from there kita dah tahu dah everything. So kita boleh dapat kita punya block diagram of governor, prime mover, rotating mass load model. So kita ada governor. Kan yang tadi tu simplified, kita ada this one is our load changes and then this one is Pmax. Ni kita punya rotating mass model kan, ingat tadi kan, output dia delta omega. Ni load model 1 over MSD and then ada load changes and then this one is from here is prime mover 1 over STCH and then input the P valve and governor punya input ialah load reference set point dengan kita ada kita punya feedback ni 1 over R ni group. So this is our complete block diagram of governor, prime mover, rotating mass load model. Okay, nama dia governor, prime mover, rotating mass and load model. Boleh? So daripada gambar ni kita boleh buat apa? Kita boleh simplify the equation when we have this load changes. So output always our output is delta omega, mana changes in terms of frequency. And then at the steady state, the governor, prime mover and rotating mass delta omega can be expressed. Is simplified by this value. Ni ialah delta omega general lah, delta omega equals to delta PL minus changes, negatekan dia, divide by 1 over R. Kalau ada banyak group ataupun banyak feedback sampai N, so everything is 1 over R, 1, R2 sampai 1 over Rn, and plus D. D is damping lah tadi. Kita nak buat ni. Boleh tak daripada sini? Cuba buat supaya dapat ni. Cuba lah. You derive equation. Biasa soalan final akan ada soalan derivation lah. Tapi biasa you boleh open book kan. You boleh biasa sudah boleh dapat markah penuh lah. Boleh? Ada soalan? Macam mana nak dirah ni? Ada soalan tak? Kita tengok contoh soalan. Sebelum kita masuk Thailand ni kita akan masuk kami ni. Dua Thailand kan. So daripada Thailand ni kita sama kalau kita tengok Thailand ni pun sama. Governor, prime mover, rotating mass load model. So and then dia ada satu feedback group 1 over R1. Dan tapi dia ada satu T over S ni. Dia ada power, sama ada power flow from area 1 to area 2 ataupun area 2 to area 1 lah. So model sama. Okay, so ada dua load lagi. So kita akan tengok tu hari Khamis ni lah. So yang ni macam mana dapat? Kita tengok contoh soalan lah. Timeline. Contoh timeline. Okay, dah apa. Okay, cubalah DIY. You dapatkan equation ni. DIY ya, cuba. Okay, ada soalan tak? Boleh faham tak? So apa yang kita belajar hari ni basically kita model everything in terms of block diagram, and we try to come up with a simple equation of delta omega. Okay, from generator, governor, prime mover, and rotating mass and load model. So this is our model for, let's say this is area 1. So for the certain generator lah. So basically what happened is your changes in terms of load plus minus ni, they can play around. Sama ada nak buka atau tutup kita punya valve and so on and so forth. So basically this is PL, this is PMAC. So this is our output delta omega, and then we feedback here to load reference set point in order to make sure that our governor sense the speed, so whether to open or close the valve in terms of block diagram. Clear? So kalau tak ada soalan, so kita stop kat sini sebab saya rasa plan lepas ni baru kita akan pergi ke tie line hari Khamis, and then kita cuba settlekan tie line, and then yang ni biasa saya tak ambil, tak masuk lah. And then kita try to look at every example of the question of previous punya soalan final. Sebab sebelum ni test hanya masuk, saya ada buat 2 test. Test 1, test 2. Test 1 look economic dispatch. Test 2 real power control. Tapi oleh kerana you punya marking punya scheme dah tukar, and then you punya pemberat untuk peperiksaan dan juga test pun dah tukar. So test tinggal 10%. Dia tukar juga CO output, CO yang maknanya kena assess you punya performance terhadap economic dispatch as well as real power control lah. So 10%. And then the next final soalan sama tapi pemakan tu lain lah. So your final is 60%, 50% kan? Berapa 60? 50 final?
60.
60. Final 60. So test 2 soalan, 1 soalan economic dispatch, 1 soalan real power control, and then 10%. Dulu saya buat 50-15, 30. Maknanya dulu ED 1 15, real power control dengan reactive power control 2 ni 15. Sekarang ni dah ubah 2 ni dapat 10%, tapi final you 60% kan. So final sama juga question 1, question 2 ni economic dispatch ni 50%. And then question 3 real power control 25%. Question 4 real power reactive power control Q 25. So everything is 50% lah. 100%. Maknanya sekarang ni kalau bagi 2 dapat this one 25, this one 12.5 lah. Okay, so itu kita punya pemakan. Hopefully you all can, because sebelum ni biasa saja ni siapa yang datang kelas, siapa yang buat assignment, biasanya budak tak dapat skor sebab tak buat assignment ataupun tak datang kelas, tak buat quiz. So kita ada berapa quiz lah? Kita ada 3 quiz je. Saya malah buat banyak-banyak. So dah ada 2 quiz hari tu kan? So supposed to be 7% assignment, 12, project 15, test 10. So hopefully sebab saya kena midterm punya BOE dekat sini 13. So kena puluh lah ni, 7 ni. Okay, never mind, tapi saya rasa memang kita akan ambil awal lah. Okay, ada soalan? Ada soalan tak kelas?
Tak ada.
Okay, tak ada saja kan? Okay, kalau tak ada kita stop kat sini. Kita jumpa hari Khamis. Kita akan tengok tie line dan juga kalau sempat kita tengok contoh. So next week kita akan discuss more on example lah. Example soalan-soalan yang biasa keluar. Okay, itu saja. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much.
Waalaikumsalam. Thank you, Doctor.
Thank you, Doctor.
Thank you, sir.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.